Yeah, so what I want to talk today about is some joint work with Magnus Carlson and Sebastian Wolf, though this is not Magnus Carlson, the chess player. And I learned today, or not today, at this conference that Magnus Carlson's coach, the chess player, part of his last name is one letter off from mine, and this Magnus Carlson is one letter off from the chess player, but there's no relation. It's just a fun fact. So yeah, I want to talk about a conjecture of Grothendieck from his anabelian letter to Faltings that is something that hasn't been so much considered. So this is a letter from the 80s where it started anabelian geometry, which is about reconstructing schemes from their étale pi1. And that, of course, you have to have very restrictive conditions because somehow, for example, you shouldn't have any higher étale homotopy groups, but Grothendieck in this letter also made conjecture about reconstructing schemes from their étale topos. Though, interestingly, many people in anabelian geometry somehow are unaware of this conjecture. I gave some talks about this before, and some experts in anabelian geometry told me, Grothendieck never made this conjecture, but I think people just stopped reading at page 6 of the letter, at page 7 of the letter. Of course, it's Grothendieck, so it's about topoi. So I'll talk about this conjecture, then some reformulation of the results using versions of conceptual completeness, and then some speculations about how some of the techniques that appear in part 2 can be used to redefine and give some new invariants in logic. Okay, so I want to explain this conjecture. And, well, I could start by just stating it, but I think it would seem kind of random, some of the assumptions, so let me try to explain some of the assumptions. So throughout this talk, I'll use the notation, if I have X a scheme, I'll write X sub et for the étale topos of X. And let me know if you can ever not read my handwriting, if it's too small or anything like this, and also please ask questions. So yeah, the general idea is to ask, to what extent is X determined by the étale topos? And for simplicity, let's work with schemes which are defined over a field. And there are kind of four, well, I don't know if they're really obvious, issues that one has to deal with in the sense that, well, you obviously cannot reconstruct every scheme from its étale topos. The first thing is you need to restrict the types of morphisms that you consider between the schemes. So you need to restrict to a finite type. So we'll work over a field, so say K schemes. Well, why? For a very simple reason that if you allow, for example, just arbitrary morphisms and you have L prime to L that's an extension of separably closed fields, well, the étale topos of a separably closed field is just sets. So they have the same étale topos, but they need not be isomorphic. So that's first issue. So if you allow arbitrary type morphisms, okay, you run into some problems. K is just a field for now. And then I will tell you you need restrictions on the field too. So that's so that's also a question which Grothendieck also asked, but it's harder, and we are on the way to understanding it, but not yet. And so I'll explain why. Number two is something called a topological invariance. So this says that if x to y is a universal homeomorphism of schemes, so what does this mean? This means that F induces a homeomorphism on underlying spaces, and also it remains a homeomorphism after every pullback. That's not automatic because pullbacks of schemes are not given on underlying spaces as pullbacks of spaces. Then the pullback x crossed over y with blank. The pullback functor on étale sites, this is an equivalence of categories. So hence also on étale topoi, you get equivalent categories. So if you're not familiar with algebraic geometry so much, you might wonder what's an example of a universal homeomorphism. So one example is if x is over fp, then there's the Frobenius. So if it's affine, you're just raising every element to the pth power. Another key example of a universal homeomorphism is you can look at a cuspidal cubic singularity, and you can resolve this singularity by normalizing it. So the resolution is just an A1, and that's a universal homeomorphism. So the thing here is you need to invert universal homeomorphisms of schemes, otherwise you have no chance of this working out. Okay. There will be 4 issues. Here's the third. And then the fourth one is something Grothendieck actually didn't realize in his letter and is not in the letter but is necessary. So you need to restrict to certain small fields. So let me just give the kind of counterexample that tells you that this type of result couldn't possibly be true over the complex numbers. So it turns out if you're smooth over a field of characteristic 0, that second problem of topological invariance disappears. I'll explain that in a second. So let's take maybe the most simple type of example where we look at K, which is algebraically closed, and of characteristic 0, and x and y over K are 2 smooth proper curves. Well, so the étale topos of the ground field is just sets. So being an equivalence relative to that is no extra condition. And one can show that the étale topos of x is equivalent to the étale topos of y if and only if these 2 curves have the same genus. But in general, there are many different algebraic structures on curves of the same genus. So this can't possibly work over C. And Grothendieck's suggestion is to work over K, which is a finitely generated field. What does this mean? This means that it is a finitely generated field extension of its prime field. So it looks like either you take a number field, so a finite extension of Q, and you adjoin finitely many, possibly 0 function field variables, or you take a finite field and you adjoin finitely many function field variables. It turns out in anabelian geometry, people have realized that you can sometimes be more general than this, like work over some p-adic fields, but well, I wasn't strong enough to prove that type of result yet. Okay, so this is all in Grothendieck's letter. So we need to restrict the field somewhat. We need to restrict to some finite type schemes. We need to invert universal homeomorphisms, which is maybe not clear how to do, and I will explain. And there's one more thing we need to do, which is not in Grothendieck's letter. And we need to restrict the types of geometric morphisms we consider. So when I think about reconstruction results, I think about two types. One is what I would call a weak or maybe just no word reconstruction result, which is saying I can reconstruct the isomorphism type of some object from some invariant. Then there's strong reconstruction results, which are saying I provide some fully faithful functor from some category to some usually very different looking category. This result will be a strong reconstruction result, and it turns out that there's more geometric morphisms between étale topoi, which are easy to see can't arise as from morphisms of schemes. So you need to restrict the topos side, which if you were thinking about a weak reconstruction result, this restriction wouldn't, I mean, it's automatic, which is the following fact from algebraic geometry, which is not a topological fact. So if you have f, say, from x to y, which is a morphism of schemes locally of finite type over a field, then, well, there are various things that are true. So one thing that's true is Chevalet's theorem. So that on underlying spaces, this map preserves constructibility. So it turns out we just need a weaker thing, which is this map on underlying topological spaces, it sends closed points to closed points. And you can show that over any field of characteristic 0, there exists some morphisms between étale topoi of very simple schemes like P1 that don't satisfy this property. So if you want a kind of reconstruction result, it's just you need this. Grothendieck didn't explicitly state this in the letter. Maybe he thought it was so obvious that. We'll say a geometric morphism f lower star from some topos x to some other topos y is pinned if when I look at the map of underlying topological spaces, so I look at the locale of subterminal objects and I take its topological space of points, which is a reasonable thing to do for étale topoi, this sends closed points to closed points. Okay. So the pinned is somehow we think of this property as like pinning down the geometric morphism in some way. I mean, this is, I don't know, just some name I liked. And so let me mention one thing in order to state the conjecture, which is a fact that, okay, maybe I should state as a proposition because it's not actually so easy to check. But we check this, which is if you have any scheme, and you look at X and Y, which are finite type S schemes. Then the groupoid, which I'll write like this, hom pin S X et Y et. So this will be the groupoid of pinned geometric morphisms from the étale topos of X to the étale topos of Y over the étale topos of S. So yeah, this groupoid is actually equivalent to a set. So if you enforce this condition of sending close points to close points, then it actually forces the groupoid to be equivalent to a set. So I state this because the conjecture I'm going to state on the next slide would not make sense without this, or it would implicitly imply this, but this is easier to state. So as Laurent was suggesting, there's this conjecture that Grothendieck gives in this 1983 letter to Faltings, which is that if K is a finitely generated field, then the functor from you start with the category of finite type K schemes, and you look at the universal category obtained by that by inverting universal homeomorphisms. Well, taking the étale topos, since it inverts universal homeomorphisms, by the universal property, it defines a functor to topoi over the étale topos of spec K, and these pinned geometric morphisms. So this side is really a 2-1 category. Because, I mean, yeah, clearly on this side I cannot represent natural transformations which are not equivalences, that this functor is fully faithful. So that's the conjecture.
Is it possible to say something about the image?
I can say some things, but I don't have a complete characterization. And it would be very nice to have one. Yeah. Yeah, this is a very good question. And I mean, it's related to something I'll say later, which is a kind of Zariski version of some of this, though not this specific statement. But okay, so the theorem that we proved with Magnus and Sebastian is that if K is infinite, the conjecture is true. And I think the infinite is because of lack of our abilities and not because it shouldn't be true over finite fields. I think it should be true over finite fields, but there's a specific, we do a ton of reductions and it involves some very involved algebraic geometry and H descent to reduce to some very specific case. And then you just need to check some very specific thing, and you learn that if your field has a non-trivial discrete valuation, you can check this via some weird trick. And it's just elementary, but not conceptual. And, well, finite fields don't have non-trivial discrete valuations. So, okay. So, yeah, what I want to do next is give a more human reformulation of this conjecture. And that, I mean, you might looking at this statement, say, well, how could you possibly prove this? Because what is this category? But it actually has a very nice description. And that's a little bit of algebraic geometry, which I think is comprehensible even if you're not a fan of algebraic geometry. So let's reformulate the conjecture. Okay. So I want to define some property of schemes that is actually pretty elementary, but kind of strange. And so it turns out that this localization will actually just be a full subcategory of schemes, which is not clear at all. So we'll say a ring A is, so the first part here has to do with this observation I made at the beginning about topological invariance. And well, if you have a cuspidal cubic singularity and you resolve it, you get a universal homeomorphism. So certainly this localization, the schemes you consider should not have cuspidal cubic singularities. So I'll define some properties of rings, and then the relevant properties of schemes will just be defined affine locally. So we'll say a ring is seminormal. I think this was introduced by Traverso. If it doesn't have cuspidal cubic singularities. So whenever you have an equation of the form x squared is y cubed in A, there's a unique element such that x is a cubed and y is a squared. So let me just give an example. If you look at the nodal cubic, that's seminormal. Neither the cuspidal cubic or nodal cubic are smooth, but this one doesn't have cuspidal cubic singularities, but the cuspidal cubic does. Okay, and the second term, I have to apologize for the name because everyone always gets upset when I say it, but it's not due to me. So if you don't like this name, you can blame it on David Ridd. It's called absolutely weakly normal. So these adjectives are used in two different ways. Weakly is a weakening of normality in commutative algebra. Absolutely is in Grothendieck sense, it's absolute. It's because people understood how to do this over a particular field, but not over Z, and this works over Z. So if A is semi-normal, and it doesn't have another collection of plane singularity types. So for all primes L, whenever you have an equation of this following weird form, which is L to the nth power, x is equal to y to the nth power, there exists a unique element that simultaneously solves this. So x is a to the L, and y is L times a. So this type of weird equation, which I think is understandable if you, it just seems completely out of the blue, was actually also understood by Grothendieck in EGA. So he studied when you have a ring extension that induces a universal homeomorphism on spectra. And he showed you can always obtain those by some successive process of adjoining elements which solve these types of equations or these types of equations. So this actually goes back also to Grothendieck. And so we'll call a scheme absolutely weakly normal or semi-normal if for every affine open, the relevant ring has that property. And here's the theorem. Who I don't really know who to attribute to. Certainly, Clark Barwick proved this. I don't know if it was known to some extent earlier, but so the inclusion of these absolutely weakly normal schemes into all schemes, this admits a right adjoint called absolute weak normalization. And moreover, this right adjoint, it identifies schemes with universal homeomorphisms inverted with absolutely weakly normal schemes. So that's what the category looks like. Now, what about relative to a specific field? So that's actually more simple. So a Q scheme, X is absolutely weakly normal if and only if X is semi-normal. That's actually easy to see. If you look at that equation that I wrote down in the second part, if you can divide by L, you just take A to be Y over L, and that's always solved. In positive characteristic, it also reduces to a more simple notion. So an FP scheme, X is absolutely weakly normal if and only if X is perfect. So this means that the Frobenius endomorphism is actually an isomorphism. Now, so this reduces to perfection, which is much somehow easier to understand operation. But let me give a reformulation of that conjecture, but I'll need to introduce a definition, which I think it will be clear to someone who has thought a lot about perfection, why this is necessary. So one fact is that when you perfect even very simple FP algebras, you ruin all finite type hypotheses. So if you perfect FP brackets T, well, what do you get? You have to adjoin all p-th power roots of T. So this is an extremely non-Noetherian ring. It's definitely not a finite type. But it's universally homeomorphic to something that is a finite type. So here's a definition. So let's say a K scheme is topologically of finite type if the structure morphism factors as a composite of a universal homeomorphism followed by a finite type morphism. So if you take the absolute weak normalization of something which is a finite type, in positive characteristic, it won't be a finite type, but it will always be topologically a finite type. Okay. And so here's an equivalent formulation of this conjecture, which is the version we prove over infinite fields. it's just any universal homeomorphism. Yeah. So you can have any universal homeomorphism followed by a finite homomorphism. Yeah.
So if you have a scheme that is equally finite, is this generalization unique or?
No, no, in general it won't be unique. Yeah, very, very much not unique. Yeah. Okay. So here's an equivalent formulation of the conjecture which we prove over infinite fields. So say you have K, one of these finitely generated fields, and X and Y topologically of finite type over K. If X is this absolutely weakly normal, so in characteristic 0, this means it doesn't have cuspidal cubic singularities. In positive characteristic, it means it's perfect. Then morphisms of K schemes from X to Y, well, I'll write it like this. This is equivalent to the groupoid, which is really a set of pinned geometric morphisms from the étale topos of X to the étale topos of Y. Okay, so I just want to give that because it's somehow a more, I think, understandable formulation of the conjecture. And this is really what we prove outside of the case of finite fields. This also gives you a formulation that if you look at these absolutely weakly normal schemes topologically of finite type over your field, then taking the étale topos is fully faithful. So really just all of the data of these schemes is determined by their étale topoi, which I think is quite a wonderful result. So let me make one remark, which is that our work builds off of some work of Voevodsky. So Voevodsky, in a paper I think he wrote maybe when he was an undergraduate, but he was reading all of these Grothendieck texts. I think he said he learned French in order to read these texts. He proved the above for characteristic 0 and X normal. So one example where what we proved includes more cases is if you look at this nodal cubic. He cannot treat that. And really his method, yeah, it doesn't work in that case. I mean, there's also some other things about this paper, like he does not check many things. He also works with some specific choice of site, which is not the standard étale site, but is only the quasi-compact separated étale site. And well, it turns out we proved that every geometric morphism between the types of schemes we consider is induced by a morphism between these particular sites. But at least what he writes doesn't obviously look like it's proving what Grothendieck said. But yeah, he also cannot treat the positive characteristic case, and there are some other things to do. Okay, any questions about this before I move on to more somehow topos theory? So if you didn't like the algebraic geometry, you can almost forget about it, and I'll kind of talk about. So I think I have 20-ish minutes left, which I think is a good amount of time. I want to maybe remind you, so this will be the section that's on some conceptual completeness. Okay, so let me say recall this theorem of Makkai and Lurie. If you are not familiar with it, maybe it's you learn it for the first time. So if x and y are coherent topoi, so if you're not familiar with this notion, this is some topos-theoretic version of being quasi-compact, quasi-separated, and having a basis of quasi-compact opens, which is a topological thing, but Grothendieck introduced this in SGA4 because the étale topos of a quasi-compact, quasi-separated scheme always satisfies this. So they provided a way of checking that geometric morphism between these types of things is an equivalence. So then the following are equivalent for a geometric morphism. So the first is that this geometric morphism is an equivalence. The second is that it is coherent. So there's some notion of some class of objects that you can define in any topos, and it's saying that the pullback functor preserves this class of objects. So certainly any equivalence has to satisfy this property, even if you don't know what this means. For the étale topos of a QCQS scheme, the coherent objects are exactly the constructible sheaves of sets. And if you look at the induced functor on the category of points, this is an equivalence. In general, this is very far from being a sufficient condition, but for these type of topoi, this is a sufficient condition. So as a corollary to this, if you put in two QCQS schemes, you get some equivalent formulation of what it means for a geometric morphism to be an equivalence. And in the context of our theorem, this coherence turns out to be automatic. So you also get an equivalent formulation just saying, if you want to know if a morphism of these types of K-schemes is an isomorphism, you can check it on the category of points of the étale topoi. And this was something that was computed beautifully by the Grothendieck school. Yes, it has enough points.
This was the first one proved by Lurie.
Yeah.
Very young.
Yes.
In fact, it is equivalent to the Gödel.
Yes. And so this, I think in this formulation, does not imply Deligne's theorem. And there was a refinement due to Makkai that I'll talk about in a second, which implies both this and this having enough points. Okay, so my point of recalling this is that if you know this type of theorem, I think this is a natural context where you ask for a reconstruction theorem. You say, can I endow actually the category of points with some more structure, which will guarantee that now I have a fully faithful functor. And there's a few different ways that you could do this. So let me talk about something that I did. So maybe the more general version of stone duality, which I sometimes like to call Hochster's version, says that there's an equivalence of categories between spectral spaces. So Hochster's contribution is there's, of course, an independent characterization of this, but these are spaces that arise as the spectrum of some ring. And quasi-compact maps, so the pre-image of a quasi-compact open is quasi-compact, and the category of pro-objects in finite posets. So usually we're used to the Hausdorff version, where you say that compact Hausdorff totally disconnected spaces is equivalent to pro-finite sets, but this is a more general statement. So we proved a kind of generalization of this where you replace this side with some type of topoi. So this is a definition in our work with Clark, Barwick, and Glasman. So we say that a topos X is spectral if X is coherent and the category of points has the following property. So this property is motivated from a fact about the étale topos of a scheme. So the étale topos of a scheme, the computation that the Grothendieck school did in particular shows that, so the objects are geometric points, and when you compute the endomorphisms of any object, you get the absolute Galois group of the relevant field. So this is a special property that makes sense for any category, sometimes called the EI property, meaning every endomorphism is an isomorphism. So for every object, every endomorphism is an isomorphism. So the category of points has that property. And the key example, as I just mentioned, is if you have X a QCQS scheme, then its étale topos is spectral. Okay. And the theory, yeah. Oh, yeah, sorry. So spectral means coherent, and the category of points has this property which makes sense for arbitrary categories. Yeah. So this is very natural from the perspective of algebraic geometry, maybe not from other perspectives. But one of the main theorems that we prove in this work, and we actually do this for higher topoi, so there's a generalization, but let me not state it, is that there's an equivalence of 2-1 categories. Yeah, you can make it into 2-2 categories if you want, but all I'll need is this. Between finite EI categories, you take the category of pro-objects. That's a generalization of the category of finite posets. And these spectral topoi and coherent geometric morphisms. And this is compatible with the following thing. So if I have a pro some type of category, I can take the limit of that pro system and get a category out. If I have one of these topoi, I can take the category of points, and this triangle commutes. So it says actually that the étale topos of any QCQS scheme is determined by a specific pro category, which refines the structure on the category of points. Okay. There's more one can say about this. Like you can describe coherent objects as functors out of this pro category and things like this. But I think for the sake of time, I just want to state this result. So that's some enhancement in this particular case of the spectral topoi of conceptual completeness. Okay, so I wanted to, yeah. The thing in the opposite direction, we call pi hat infinity 1. There's a reason for this. maybe let me not explain that now. But that one's the one that's harder to actually describe explicitly. So I wanted to state some theorems about this, which is, so the last talk yesterday talked about this shape theory, and from this invariant you can recover this shape. So now I'll start turning on the homotopy theory because that's something that I like to do. So I'll write B from infinity categories to infinity groupoids or spaces for the left adjoint to the inclusion. So meaning you invert all morphisms in your infinity category, also called the classifying space, which is why I write it as B. And so you can extend this to a functor on the level of pro-objects. And another theorem that we prove is that for X, a spectral topos, if you take this pro-1 category, you level-wise apply this classifying space construction, you get a pro-infinity groupoid, and it's exactly what is called the shape of X. In the particular case that X is the étale topos of a QCQS scheme, this gives a very explicit description of the étale homotopy type, and you can actually use this description to prove some things that people didn't know. Another corollary here is that if we have one of these K, which is an infinite finitely generated field, then the functor from the types of K schemes that we can reconstruct to these types of pro-categories with some restriction that sends X to this invariant of its étale topos, this is also fully faithful. And if you unpack what this invariant means, it's a very concrete, somehow, statement. And it's saying that you can really reconstruct the scheme from basically the Zariski space along with the data of all Galois groups at every point with their topologies and some ramification data. Okay, so I have 5 minutes. Is that about right? Okay, so I think I maybe just have enough time to say some speculations on logic. So what I want to do is give some reformulation of this result using condensed mathematics. So this is how I got into this, actually. So a reformulation of this result that's maybe not obvious that it's a reformulation, but it is that the functor, if we look at from spectral topoi, from any spectral topos, I can get out a condensed category by doing the following thing. I send X to, well, I need to say where to send every extremely disconnected compact Hausdorff space, and I say send it to geometric morphisms in the pullback direction that are coherent from X to sheaves on this compact Hausdorff space. This is fully faithful. So this is some natural a extremely disconnected compact Hausdorff space. So I need to write down a product-preserving presheaf of categories on this, and this is such a thing. Now, when you take K to be the point, this is exactly the category of points, because it turns out for these types of topoi, every point is coherent, which is not always true. So that's some maybe interesting other invariant. And it's related to something that Jacob Lurie did, extending work of Makkai. So, extending Makkai's strong conceptual completeness theorem, he proved that the functor from coherent topoi and all geometric morphisms to condensed categories that I'll call now point underline, that sends X to the same type of thing, but I don't look at coherent geometric morphisms, I look at all of them. This is fully faithful. So he showed that this is one way to encode the ultra structure on the category of points. Now, what's the difference between these two things? Well, for the spectral topoi, you can reconstruct from the smaller amount of data of only coherent geometric morphisms. But for other coherent topoi, it's not reasonable to suspect that you could do this. Like if you take X to be the classifying topos of abelian groups, then when you look at coherent points, these are just the category of finite abelian groups. If you look at all points, it's the category of all abelian groups. And yeah, you cannot reconstruct the category of all abelian groups just from finite abelian groups. So you shouldn't expect that that first thing would be fully faithful for all topoi. Okay. So I want to finish by explaining some speculation about the relationship to logic using this thing, and it's related to this description of the shape. So here's the notation. So say I have T, which is a complete first order theory. In logic, people defined a long time ago something called the Laskar, well, Laskar defined it, group, gal L of T. So it's a topological group, and it depends on a sufficiently saturated model of your theory. Let me also write mod T for the category of models in sets, which recall is the category of points of the classifying topos of the theory. Now, there's this wonderful theorem that gives a reinterpretation. So, I mean, Laskar's definition was very somehow explicit. A reinterpretation of what this Laskar group is in terms of the fundamental group of some classifying space. So what they show is that as a discrete group, this Laskar group, it's isomorphic to the fundamental group of the classifying space of the category of models, pointed at the sufficiently saturated model. So you may wonder, once you have that isomorphism, you say, hey, this classifying space, it might have higher homotopy. In general, it does. For example, like if you look at one of these topoi or theories that's classifying like cyclically ordered sets or something like this. Now, you may want higher invariance, but this is a topological group, so how do you improve that structure? And that's what I'll finish with, which is a question. So There's also a condensed classifying space. So if you input a condensed category or infinity category, you can output a condensed infinity groupoid. And you just apply classifying space to each term. And since classifying space preserves finite products, this defines a condensed object. And so the question that I have so far been unable to get any logicians to think about, but I would really like to know the answer is, so in any infinity topos, you can talk about homotopy sheaves. So I can take the condensed fundamental group of this condensed classifying space of this fancy version of the category of points, which is a condensed category. And what I would like to know is, so there's a functor from topological spaces to condensed sets. So you can think about this topological group, that's the Laskar group, as a condensed group. Are these isomorphic? Or maybe they're not isomorphic, but can you at least obtain this one from this one? Okay, so I'll finish here.